I'm Kanad, and we're learning about, well, we did our project on two different things. One was vertical seepage measurements in a lake, and another is examining the concentration of methyl mercury.
So we worked with Roger Pacheco Castro in vertical seepage measurements in a lake, and we worked with Serena Pham in examining the concentration of several methyl mercury species.
All under the supervision of Dr. Mingye.
Okay, so first up with Mr. Pacheco, we did two preliminary experiments. We did a Darcy and a Porosity experiment. The Darcy experiment was in order to determine the permeability of this particular type of sand, which we needed in order to accurately measure the flow in the big tank experiment that we were going to do.
Yeah. One of the things that we need, the Darcy is essentially the father of Darcy's law.
And hydrogeology.
Yeah, he created a law that basically implements the factors into what flowing water is. So we were trying to test that out using the tubes, and one of the subsets is that we needed the porosity of the sand, because a lot of times people assume that the sand grains are uniform, and that's why there's a lot of complications. So we had to, but it's not always the case. For example, this grain of sand, this bag of sand could have multiple size grains, which could affect the outcome of Darcy's law. So therefore, we had to conduct a small mini experiment for the porosity lab, where we found the porosity of the sand.
So once you determine the K value, which is how the water flows, so it's typically denoted in feet per mile per day. So it's the diagonal flow of water. We actually used ModFlow, which is another it's a geophysical program using Python, which allows us to model groundwater and surface flow.
Based on the graph here, you see that the red line on top is the ModFlow software when we put in the specific parameters, and the orange line here is our experimental data. Now, what we're trying to find is K, which is the permeability. So Darcy's law here is Q over A, which is the rate of flow in a given area, is equal to negative K times the derivative of dH over dL, which is the
difference in head.
Yeah.
Difference in head over the length of the tube.
So if we put the Q and A on one side and the DHDL on the other, the slope is what we find.
And the slope is K.
So as we can see, the model for ModFlow was able to accurately predict what we got in our experiment.
And we got pretty consistent results. So this is the big tank that I mentioned earlier. It's found in the Keene building, the basement in the Department of Geophysical Studies. It's filled with about 150 pounds of sand. If you see the two red lines in on the rightmost corner, the bottom line signifies the surface of the lake, and the top line signifies the height of the water when the lake was fully filled. On the bottom left corner, you can see the apparatus we used, which we kind of had to build because we couldn't get accurate, consistent results at first, so we had to find a way to measure it, and we ended up building that, which we used to measure how much flow the lake was, how much flow there was at the surface of the lake.
So basically what we did with this lake setup was we took the flow at different places within the lake on one dimension. And the orange, of course, is
at one point, and the red is at a different point. What we saw was that the results were not consistent because the sand was not evenly packed. This again goes back to the point that we can't really get evenly packed sand. So what we did in order to account for that error was that at the same point in one dimension, we moved the tube with which we measured the flow in the perpendicular dimension, and this is the result we got. So originally we hypothesized before taking the data from the second point that the error would be consistent linearly, but what we found was that you'd have to take the error at each point because the flow would be affected differently at each point. In addition to that, we did speciation modeling.
Yeah, speciation is basically the distribution of a chemical through a set of species, chemical species within a system. And using speciation, we can control the concentration of the products based on the concentration of the reactants. And we can also trace it. And using the process of speciation, we can find things in our environment, such as the toxicity of a chemical or the bioavailability of a certain chemical in the environment. Now, we use the software FreakC, which is a aqueous geochemical speciation software. And it can do stuff like equilibrium reactions and thermodynamic data. Basically, it has all constants of, we insert constants that are gained experimentally, and from there, it can model reactions as if it was in an environment to an accuracy that can go undetected by experimental methods. So, our case study, like what we were doing specifically with speciation, would be the analysis of methylmercury. In Oak Ridge, Tennessee, there were some nuclear experiments, like nuclear weapons experiments that were going on, and because of that, methylmercury started to get introduced into the environment. And methylmercury is very dangerous.
It's a neurotoxin which, if you come in contact to, you can die within a year, but if you ingest, you can die within a month. So as we were studying what kinds of parameters would cause the methylmercury concentration to increase.
So basically, we were using FreakC, the software. We were able to examine certain percentages of certain compounds. So as the pH goes up, you can see the relationship of certain chemicals. And that we also applied that to temperature. So you notice here that this graph is from 0 to 100%, and you're able to see the two dominant chemicals as the temperature rises. But using the FreakC software, we can even go to 100th of a percent of the availability of certain chemicals. And that's something that is very hard to detect via experimental methods because it's hard to replicate these things. And we found that of all the things, as you increase both the pH and the temperature, one chemical stands out as increasing, and that is methylmercury hydroxide.
So in our conclusions is that we found that there was a major difference between the results that we got from our tank experiment and ModFlow. Our difference was approximately 3 times the results that ModFlow got. So there was either our methods had a large amount of error, as that model can be, since it's such a small model compared to an actual lake. Our actual meddling with the model of inserting the tube to measure the flow caused more error than we expected, or we messed up in inputting things in the program. So there was those problems that we arose, but it was consistently 3 times more than the points generated by ModFlow.
And that's the two major things that we did, the speciation software and the groundwater flow. While they're different conceptually, what we did with them are similar. We basically use software that emulates it because it's hard to predict or to
take actual value, actual data in real world, because it's very difficult to use instruments and you don't always have access to all the elements or all the points in a lake.
Thank you.